Hey guys, thanks for logging in and watching this second to last video actually of the year. So our second to last lesson is about solving log equations. If you didn't get that logging in joke, well, I guess you get it now. So hopefully by the end of this, you're feeling more comfortable and we're getting closer to becoming LumberJacks and stuff like that. So let's get started about how to solve a log equation. Before that, here's a good little joke. I feel like the more you learn about stuff, the more you can appreciate puns and you can appreciate just humor in general. If you don't get this joke, or the idea behind it at least, you don't have to think it's funny, but this is kind of a big deal to know, right? These are two most popular types of logs, the ones with the base E and the one with base 10. All the other logs can have any other base. Yeah. So we have three different cases that I'm going to show you on how to solve logs. Our first scenario here is where we have two logs equal to each other. And by that, I mean I have a log on the left equals a log on the right. Notice how these two logs have the same base. So I chose pi as 3.141592653589793238462642338. If you give me a beat, I can go forever with this. Anyway, I'm showing you this random number because as long as the bases are the same, no matter what they are, we consider these two logs to be equivalent, which means the value on the inside should also be the same. What's great about that is that if I know that they're the same, I can remove the logs and just solve the inside by itself. I can just solve 4x minus 7 equals 5. And now that the logs are out, this is basically an algebra 1 problem. We move the 7 over, we get 4x equals 12, divide both sides by 4, and x equals 3. Now, before we confirm that this is my actual solution, we need to make sure that, as always, when we're solving an equation, that we plug it back in and we check our solution. So we need to plug it back in here and verify that it's correct. So here we have log base pi of 4 times 3 minus 7 equals log base pi of 5. 4 times 3 is 12. So we have 12 minus 7 is 5. So log base pi of 5 equals log base pi of 5. Since the left-hand side equals the right-hand side, we have a solution at x equals 3. Let's try another one of this same case, but it's a little bit more complex. Not in the solving, but in the understanding. So here we have, again, two logs that have the same base. Log base 6 and log base 6. So these two values must be equivalent. So let's set it up and solve. 2x minus 1 equals x minus 2. We're going to solve for x by moving everything to the left. We're going to move the x first. We're going to subtract x on both sides. We're left with x minus 1 equals negative 2. Move the 1 over. X equals negative 1. So we're going to naturally put this back inside and check that the solution is true. So on the left side we have log base 6 of 2 times negative 1 minus 1 equals log base 6 of negative 1 minus 2. 2 times negative 1 is negative 2. Sorry, we have the log base 6. Log base 6 of negative 2 minus 1 equals log base 6 of negative 3. Notice how log base 6 of negative 3 equals log base 6 of negative 3. Now, yes, Although here we have the log base 6 of negative 3 equals the log base 6 of negative 3, here we have a no solution scenario. This is extraneous. This does not exist. And I'm going to explain to you why. A few videos back, we spoke about, when we introduced logs, we spoke about how they were inverses of exponential functions. Now, the exponential function looks like this, right? And the log function, so this is e to the x, or 10 to the x, or anything to the x power. The log function looks something like this because they're inverses of each other. Now, if we just focus on the log function, notice how we have the x values and the y values, right? What is it that it can exist in this function? We have negative y values exist, but only positive values for x can exist in the log equation. Very similar to a square root function, right? We can't take the square root of a negative number and have a real solution. Then the square root function looks like this, right? We can't have these negative values over here inside of a square root. This is a square root function. This is why in the very beginning of the year, we did a unit called parent function. We did a big foldable, it's like orange, green, yellow, or something like that. And we put all of the equations in there with all of the graphs and all the pictures to understand what the parent function looks like and how it behaves. Notice how we cannot have negative x values. Now, there's nothing wrong with getting a negative x as an answer. The problem is when you plug it back into the original problem, if you end up with a negative log, sometimes plugging it back in gives you a positive log, and that fixes the solution. It's no big deal. But if you plug it back in and you get a negative log, now you're dealing with this side over here. You cannot plug in a negative 3 and exist. So notice how there's nothing over here as an output. So this function does not exist, or this value does not exist. You can put DNE for it does not exist. You can put no solution. You can put extraneous solution. Whatever you like. All right, let's move on to case number 2. Notice how here we only have one log. So in these next 2 examples, I'm going to show you how to solve for a function that has only one log. Now, before, we had a log on each side, and we could just cancel the logs. Here we cannot do that. Here we have to go back to the definition of what a log is, and how do we convert from log to exponential. We did this back a few videos ago. I believe it was last week's videos where we spoke about how to convert back and forth. It was two ago, okay, and how to convert them. So what we do is we take this base and we move it over to the other side, right? And we change it to exponential form. So on the left side, the log disappears, and we're left with 4x plus 9 equals 7 squared. This is from the rule of the definition of a log, okay, where we said the base moves over to the right and it pushes as an exponent. Now here, now that the log is gone, right, we can solve for x. So on the right-hand side, we have 49. We have 4x plus 9 equals 49. To solve, we move the 9 over. 4x equals 40. Divide both by 4. And you're left with x equals 10. Again, we have to confirm that this is correct. Right? We need to confirm that this is actually a solution. We're going to plug it in. We have log base 7 of 4 times 10 plus 9 equals 2. So we have log base 7 of 40 plus 9 is 49 equals 2. Are these 2 statements correct? Well, if we convert this, again, log to the other side, we have 49 equals 7 squared, and that is true. This is why it's so useful to be able to convert from log to exponentials, that you can get rid of the log immediately. So because this is correct, we have our self-solution at x equals 10. Let's try one more scenario in this same case. Here is a little bit more complex, right? We only have one log on each side. We only have one log on the left, right? So we're going to be trying to convert it from log form to exponential form. But for us to be able to do that, we need to get rid of this plus 1 and this times 2, right? We need to isolate log. We want to leave this log by itself so we can then convert to exponential form. So whenever you're solving, as always, we want to be able to do PEMDAS backwards, which is SADMAP. So we start with addition and subtraction. So I'm going to move this one over, and we're left with 2 times log base 3 of 4x minus 5 equals 6. To get rid of this 2, on the front, we're going to divide by 2 because we're multiplying. So you can divide the left and divide the right. You're left with log base 3 of 4x minus 5 equals 3. Now that you're left with the log by itself, now that it's alone, and there's nothing in front of it, there's nothing behind it, and it's just by itself, now you can take this 3, move it over, raise this as an exponent, right? Push that to the top, and we can get rid of the log. So we get 4x minus 5 equals, that becomes your base, and this right here becomes your exponent. This 3 becomes your exponent, so we have 3 to the 3rd power. We have, I'm going to move some stuff over to make some space. So we have, let's see, 4x minus 5 equals 3 cubed. This 3 cubed is going to come down to 27 because it's 3 times 3 times 3, right? A lot of people think it's 3 times 3 is just 9. No, but it's 3 times. So 3 times 3 times 3, and that's 27. So we have 4x minus 5 equals 27. We're going to solve for x. We're going to move the 5 over. 4x equals 32. Divide by 4 on both sides. And you get x equals 8. As always, let's plug it back in here and see if it is correct. So we have 2 times log base 3 of 4 times 8 minus 5 plus 1 equals 7. So inside the parentheses, we have 4 times 8 is 32. 32 minus 5 is 27. So we have 2 times log base 3 of 27 plus 1 equals 7. I need to evaluate, since I only have a number in here, right? I can actually find the value of this log. Log base 3 of 27 means something, right? This log base 3 of 27 equals 3. Now, I've learned to find some tricks where I can figure out the base to what exponent gives me this is going to give you the value of that 27. So 3 to the 3rd power is 27, and that's how I can simplify a log a lot faster. Now, I'll show you here on the right what I did to find the value of this piece. I did this in my head. Log base 3 of 27 equals something. Because there's no x value inside that log, the log of a number will always be another number. So I took this 3 and I converted it to exponential form. I did 27 equals 3 to the what power? So that what power is 3. And that's how I can replace this log with a 3. So basically, we have 2 times 3 plus 1. Just make some space so you can see the rest. So I have 2 times 3, which is the value of this log, plus 1 equals 7. 2 times 3 is 6. 6 plus 1 is actually 7. So because 7 equals 7, we have ourselves a solution at x equals negative 8. Sorry, x equals positive 8. All right, let's go for our last case in our last scenario, and then we'll call it a day. In this last case, now we're going to introduce more logs into the picture. The first case, we had a log on each side. The second case, we had only one log, and here we have multiple logs on different sides and multiple sides and all kinds of scenarios. Okay, so what we're going to do here for this third case is I'm only going to solve the problems. If you want to do extra credit, you can definitely solve and show me how these are solutions or no solutions by plugging it in yourself and submitting that work to me through email. So if you send me the work for these next 3 examples, proving that they are correct or not correct, I can give you some bonus points on quizzes or any low assignments that you have. All right, so let's get started. Here, we're going to have to condense. Our goal is to simplify this whole equation and make it smaller. So if on the left side you have multiple logs, you're going to want to combine them and putting them together into one log only. And we did a video the last week on condensing and expanding log using properties, right? The last assignment before this one, this is where it kicks in. Okay, so we spoke about the product rule when we have 2 logs that have the same base. This is base 10, this is base 10. When 2 logs have the same bases, they're considered like terms. We can combine these 2 logs through the product rule. Product rule talks about the addition. So if you're adding, you can multiply the inside and combine them into one log. And we're going to do just that. We have the log base 10 of 8 times 2x plus 1. We're multiplying them. Now we just condense it to something shorter. We're going to distribute here real quick so we can make something a little bit simpler. We have the log base 10 of 16x plus 8 equals 2. And now we're back to case 2. Case 2 said that to get rid of this log, we take this base and we move it over as an exponential form. Remember, when it does not have a base here at the bottom, when you don't see any number, when it says log and you don't see any number, you assume that it's 10. If it's a natural log, it's also not going to have a number at the bottom. But natural logs have base e. So a natural log would be considered log base e of x. Okay? So we take this base 10 and we move it over. The log disappears. We have 16x plus 8 equals 10 squared. 10 squared is 100. So 16x plus 8 equals 100. Solve for x. Move it over to the other side. 16x equals 92. When you divide both sides by 16, you're left with x equals 6. Okay, now, is this a solution or is this not a solution? I want you to go ahead and plug it back in, check to see if this works, and then check to see if this is an actual solution to the problem. And you can do that for extra credit. Example number 2. We're going to do another one where we have multiple logs and we're going to use these properties. As a quick refresher, remember that subtraction is associated with division or the quotient rule, right? So we want to be able to divide the left-hand side and the right-hand side because they have the same base. When they have the same base, you're considered like terms. So I'm going to rewrite this as log base 2 of 3x minus 1 divided by x equals log base 2 of 17. See how we condensed the left-hand side to make it smaller? Now, this is back to case 1. Case 1 said when we have a log on each side, because these 2 logs have the same bases, then the inside must be equivalent as well. So I can drop the logs, no pun intended here. I can drop the logs And unless you're in the restroom watching this video. If we drop the logs, we now have 3x minus 1 over x equals 17. And now it's about solving for x. We're going to multiply by x on both sides. 3x minus 1 equals 17x. Move the 3x over. Negative 1 equals 14x. Divide by 14 on both sides. X equals negative 1 over 14. Now, our job is to plug this back into the original problem and see if it actually is a solution or not. Okay? Remember, not all negative values are no solutions. So we have to plug it in and see if we're taking the log of a negative number, that's when it becomes a no solution. So if we have the log, when you simplify everything, the log of something negative, this is a no solution scenario or extraneous solution. Because we got a solution, it just became extraneous. All right, last example. Okay. Why don't you go ahead and try this last example on your own? I saved the best for last. All right. Hopefully you pause that and you tried it yourself. If not, let's do it together. Here we have the product rule because we're adding two logs that have the same base. So we're going to multiply these two together. Now, when you're multiplying them, you're going to have log base 18 of x plus 5 times x minus 2. X plus 5 times x minus 2 needs to be simplified using box method. Because you're multiplying two things, right? You're doing distributive property 2 times. So make sure you do box method for this. I'm going to save some time and I'm going to skip to the next step because I'm going to do this in my head. We have log base 18 of x squared plus 3x minus 10 equals 1. Notice how now we only have one log on the left side. Because we have only one log, we can use, I believe it was case 2, where we take this base, we convert it to exponential form, the log disappears, and you're left with x squared plus 3x minus 10 equals 18 to the first power, or just 18. Notice how here we have a quadratic. So to solve for x, we're going to have to factor. We're going to want to do our 3 columns, and we want to be able to find our 2 solutions for x. So here I'm going to move everything to the left so that I can have my 3 columns. This has to equal 0 for the 3 columns to work. So I'm going to subtract 18 on both sides. We have x squared plus 3x minus 28 equals 0. Now, your 3 columns here, I'm going to show you on the left what it is in a little bit, but I'm just going to tell you the answers. I know that 4 times 7 is 28, and 4 and 7, if you find the difference, you get positive 3. So we get, our solution comes down to, or our factors are x minus 4 and x plus 7. Those are my 2 factors. I'll show you how to get those here in a little bit. We set each of those factors equal to 0. So you get x minus 4 equals 0, and x plus 7 equals 0. When you solve for x, we're going to move this over. We're going to move this over. You get x equals 4, and x equals negative 7. Again, you need to plug both of them to the original problem to see if they are solutions or not, and that's your extra credit. Now, to show you how I got this as a quick review from the second 6 weeks, we do our 3 columns, right? We have x squared plus 3x minus 28 equals 0. Our 3 columns means the factors on the left, we have x times x. The factors on the right, we have 4 times 7. Now I have a negative 28 as an answer, so one of these has to be negative. I'm going to place the negative on the 4 because when I cross multiply, I have negative 4x and positive 7x. The sum of these two gives me a positive 3. And I want a positive number, not a negative number, so I put it on the negative 4. Okay, now that I've checked my work, my factors are x minus 4, x plus 7. And that's how I got this piece. So hopefully we can do this stuff on the side that I wrote in black in our head, or be more comfortable finding these factors by now. But yeah, these are my two solutions, x equals 4 and x equals negative 7. If you want extra credit again, remember to submit these to show that they're solutions, if they're both solutions or just one of them, to prove that they are solutions or not solutions. Alright guys, I hope this helps. We're coming down to the very end. Make sure you're submitting your assignments on time. Make sure you catch up now, not later. It's going to be impossible to catch up. And then you're going to even know what your grade is going to be if you wait to the last minute. So when you submit your assignments late, it's going to be really hard for you to know where you're going to end up, right, until the last minute when I start finishing grading all these things. So get them in now. Get your grades in now and feel comfortable and know that you can finish school even a week early versus a week late. All right. You guys have a great day. I'll calculate later.